Welcome to section 9.1 numerical expressions for chapter 9. Pause this video often, taking notes, doing the U-tries on your own, and doing the examples along with me. Here are the topics and the objectives that we'll be covering in this section, as well as the standards and key concepts and vocabulary. So what are mathematical expressions? Expressions are calculation recipes that show us how we should be calculating an expression. It can summarize a multi-step calculation compactly and help us see and analyze the structure of a calculation. Sometimes we've got variables like x and y, others are just numbers. That's what we're going to be talking about in these videos, are the numerical expressions without variables. We'll see that we can usually depict expressions with patterns, and we can actually write different expressions to model the same total. A numerical expression is a meaningful string of numbers with operations. So we've got addition, subtraction, multiplication, division, exponents, but there is no equal sign. So that is something that is pretty important here, that when we talk about expressions, they are different than equations. We are not going to have an equal sign with these. So 2 plus 3 is an expression, 3 times 5 is an expression, 35 divided by 7. We can also have more complex expressions with multiple operations, and we'll take a look at those as well. So to interpret the meaning of an expression, we must use the conventions of the order of operations. So when we talk about 3 plus 7 times 2, that means the sum of 3 with the product of 7 times 2. So the sum, this means sum, of 3 and 7 times 2. And then when we look at this, we have the sum of 3 and 7 times 2. So this is the product of 3 and 7 with 2. So when we're evaluating a numerical expression, that means we're determining what it equals. Now, again, there is no equal sign, but that is what we are determining, the value of an expression. And we're going to use the order of operations. So just a quick reminder here, I actually use GEMS instead of PEMDAS. I actually really do not like PEMDAS because PEMDAS says that multiplication before division, addition before subtraction, but GEMS makes you think a little bit more. We're going to do grouping symbols, so that's going to be our fraction bars, our brackets, our parentheses, our exponents, and then multiplication or division from left to right. So they are equal, and we go from left to right. Same with subtraction or addition from left to right. So let's do a couple examples here. So here I'm going to look at GEMS. Do I have any grouping symbols? Nope. Exponents? Nope. Multiplication or division? Nope. Subtraction or addition? Yes. And I'm going to go from left to right. So when I come from left to right, the first operation I see is subtraction. So I'm going to circle the subtraction and bring down the plus 3. 9 minus 7, we get 2. And then we only have one operation left, so that gives us 5. And then why do I call it GEMS? Because we can make a cool gem at the end. All right, let's take a look at this example here. So again, I'm going to go through GEMS. And I do have a grouping symbol. This fraction bar is a grouping symbol. So from here, I'm actually going to rethink about GEMS again. So in this grouping symbol, do I have any more grouping symbols? No. Do I have exponents? No. Multiplication or division? No. Subtraction or addition? Yes. So I'm going to do this operation first. So I'm going to bring everything else down. So 2 plus 3 is 5. And now I've done my grouping symbol. I don't have exponents. I do have multiplication or division. This is a division sign. So I'm going to do 20 divided by 5 first. That gives me 4. And I'm just left with one operation. And so I get 3. Finally, let's do this one over here. So we do have a grouping symbol. We have these parentheses here. But inside of that, we have more operations. So inside of this, I don't have any grouping symbols, but I do have an exponent. So I'm going to bring this down. I'm going to keep my grouping symbol because I haven't dealt with it yet. 1 to the third power stays 1. 1 times 1 times 1. 1 times 1 times 1. And now I've dealt with my exponent. Inside my grouping symbol, I have one operation left. That's addition. So I'm going to do that next. When I handle the whole grouping symbol, I don't need to bring it down anymore. And 5 minus 3 is 2. Oh, look at that. There we go. And we get a gem. All right. And go ahead and give these 3 problems a try. Video and press play when you're ready to see the solution. And check your work against mine. So how do we interpret and evaluate numerical expressions? We're going to break them down. So we're looking for addition and subtraction. Those are last in the order of operations. So we're looking to break them into components combined by addition, subtraction, or both. So when we look at this complicated expression here, we have addition breaking this up into two terms here. So this is the two terms, 1,000 times 5 and 20 divided by 4. So we want to actually learn to see the structure without evaluating. So can we tell whether this would be even or odd? And if we look at the structure of it, we would say, okay, we are going to multiply first. So that's going to make this an even number because we're going to multiply it by 2. And then at the very end, we're going to add 1, which would make it odd. So when we can analyze the structure of an expression without evaluating it, it helps us understand the meaning. So now here we're going to determine if these expressions are equivalent or different without evaluating. And we're just going to take a look here. So let's look here. We've got, this is a plus. And what this is saying here is this is the sum of 3 and 14. Okay, we've got another sum here. So this is the sum of 3 and 14. So far these are the same. Let's see about, this is the sum, but it's not the sum of 3 and 7 times 2. We've got our grouping symbol here. So what's going to end up happening is this is talking about a product because we're going to do this times that. So this is 10. This is the product of 10 and 2. This one is different. So without actually finding the value of the expression, we can determine if expressions are equivalent. So let's analyze the structure of this expression here. Basically determining the terms is what this is asking, determine the terms. So we're going to take our order of operations and just kind of look at it without evaluating it. So we see our grouping symbol here. We see our exponent here. And we would do those, and then we would do our multiplication. So we're multiplying that. We would do our division from left to right. And there we go. So we can see that when we separate these by addition and subtraction, we get our terms. So this here is a term, and this is a product because we're taking 3 times this group. And this here is a term because it's separated by addition and subtraction, and this is a quotient because we're dealing with division. And here this is a term, and this is also a product because we're dealing with multiplication. So if you want to see it a little bit more, you can pause here or check it out in your textbook. So go ahead and analyze the structure of this expression, plus press play when you're ready to see the solution. And there we go. So here we're going to actually write 2 different expressions for the total number of dots in the designs, and we're going to show or explain why they work without evaluating them. So let's take a look here. So we've got these dots. So we've got, let's take a look at the diagonals here. So we're kind of looking in this direction. We've got 1, 2, 3, 4, 5, 6, and we've got 1, 2, 3, 4, 5 at the little ones. And then we've got 1, 2, 3, 4, 5, 6, these big ones, 1, 2, 3, 4, 5. So if we take a look, these longer ones are going to be 6. So how many of those do we have? 1, 2, 3, 4, 5, 6. So we have 6 diagonals of 6 dots. And then also we have, how many of these? We've got 1, 2, 3, 4, 5. We're going to have 5 diagonals of 5 dots, and that would cover all of the dots. Well, how could we look at this in a totally different way? Well, maybe we look at this as in half horizontally. So if we have half horizontally, we would have over here, we would have 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7. I see a pattern. 1, 2, 3, 4, 5. These look like odd numbers. So on this side, I know I've got 1 plus 3 plus 5 plus 7 plus 9, and I know it's going to repeat on this half, so I'm going to multiply that by 2. Now that'll cover all of these, right? But it won't cover this middle row, but I could just add that in. What do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, which you may have guessed because of the odd numbers. And that would be two different expressions for the same thing. Go ahead and give these 3 problems a try. Press play when you're ready to see the solution. And we'll pause there and continue in our next video.